Hello and welcome to another Java tutorial. In this tutorial I'm going to continue the discussion on numerical integration using Gauss-Legendre quadrature method. And we said that when we're trying to solve the problem of integration over -1 to 1, the quadrature points xi and the weights wi's have closed form solutions. Xi's are the roots of the Legendre polynomial of degree n, and all the roots of a Legendre polynomial are distinct roots. They are all real roots and they have odd parity. So if, for example, we look at the third degree polynomial, it should have a 0 root, and then the other two roots have opposite parity, plus and minus. They equal and opposite. Okay, so all the roots are real, distinct, and all of them are in -1 to +1. So maybe I'll write it here. All roots are in -1 to 1. And we also said that the Legendre polynomial, based on the definitions that we discussed, like the Bonnet or Rodriguez, they might result in so based on the definition what we choose, we might not get this normalization. So the weights have this equation. Only the Legendre polynomials are normalized at 1, at the endpoint, right, to be 1. So, and now what we are going to do is we also calculated, we implemented these two methods, the Bonnet's recursion formula and Rodriguez formula, by extending our polynomial class to be able to take the nth derivative, and also taking a polynomial to some power, raising it to some power. And now what we are going to do is we're going to implement the general Gauss-Legendre polynomial with n points. So we should be able to find the roots of the Legendre polynomial and also the weights. So let's head to Eclipse. So in our demo polynomial package, we already have this Legendre polynomial that has two methods, from Bonnet and from Rodriguez. And in the integral 1D, what we are going to do, we're going to create another method, public static public double Gauss-Legendre. And then we're going to have double start, double end, and int num points, number of points, or num quadrature points. And then, so what I'm going to do, I'm going to create a variable n, num quadrature points. We actually don't need to, just call it quadrature points. And then here, what I'm going to do, remember what we're trying to do here. We're trying to integrate over a start to n. So we have to do the mapping first, create an integral function, which is called the map function, and maps the original integral function to -1 to 1. And then the rest is basically the same here, right? And the only thing that is different, maybe let me just write it. So double weights, new double, we have n quadrature points, so n weights, and double quad points. Let's call this points, just points, and new double n. All right. And okay, I'm going to also put this here and create weights and points, and then integrate over -1 to 1, and then scale to interval start end, and the way we scale it with n minus start over 2. So so we're basically having the same thing here. We create the sum, we do a for loop to integrate over -1 to 1, and then scale it back to a start end by doing n minus start over 2, right? Half of the length. Now what we need, now we need to use our Legendre polynomial to create the weights and points. So what I'm going to do, I'm going to give this a dependency on the polynomial project. Demo polynomial. Let's also remove the dependency on the mathlib, and here I was using this timer class, so let's also comment this out. We also have the export, so let's also remove the export, Command Shift O. Okay, now we need to create the weight. So we said that the Legendre polynomial, so we're going to create the Legendre polynomial. Polynomial Legendre n, or Legendre is Legendre polynomial. Let's use the bonnet, which was recursive, and then we are going to use n, which is the quadrature points. All right, and then here we're going to get the roots, and so and the weights. So for int I equals 0, I less than weights dot length, or it's just n, right? I plus plus weights dot weights I equals what? So what we need to make sure that here is to normalize it. So Legendre equals Legendre divided by Legendre evaluate at 1. We gotta make sure that we normalize it to its value at 1, although most likely it is 1. All right, so weight is 2 divided by 1 minus points I squared. Okay, so let's go back to the definition. 1 minus xi squared times p prime xi squared times so maybe let's double c1, 1 minus point I squared and then double c2, and then eventually weight is equal to, weight I is equal to 2 over c1 times c2, and c2 is basically Legendre. We're going to take the derivative and then evaluate it at points I, right, at xi. I could just let's also do a refactoring to make it easier. All right, so this brings it closer to the actual equation, weights and x, and okay, maybe let's just keep it like that, points and weights. In the points 1 minus point I, so 1 minus xi squared, 1 minus xi squared, and here I'm calculating p prime order n, okay, p prime at xi, and I have to square it. So let's call this double C3, C2 times C2, and here we put C3 as the weight. All right, so that's it. But now what we need to do, we need to get the roots first. So normalize it, get the roots, get the weights. So how do we do that? We call the Legendre dot roots, right? Now this is absolutely not the most efficient way of getting the points. There are other algorithms that are better in terms of approximating the quadrature points and weights, but here I'm just calling it just the roots and finding the roots. And this roots method, if you recall, this returns a complex. So let's go back to this method. It has the complex type from the Flanagan package, which is in our mathlib. In one of the reference libraries, we have this Flanagan here. So I'm just going to use this. Access modifier, so complex C roots or complex roots, all right, but then I need to have a dependency on it, so I'm going to add a dependency on the mathlib, and now it finds it because in the mathlib I have added if I go to the mathlib build path in the export, I have enabled the mathlib project to export Flanagan package, right? So when I add a dependency on the mathlib, it already adds a dependency on the Flanagan package as well, all right? So we are getting the roots, but these are complex, and we already know that all the roots are real. All the roots are real, all right? So what we are going to do, actually we can test this. So let's go to test polynomial. Actually test diff public static void test 6, for example, and then Legendre polynomial, let's say we get the 6th degree, and we get the root, all right? And then for complex, or maybe for int I equals 0, I less than c roots dot length I plus plus, we just do the sys out on the c roots, and they should all be real. Test 6, let's invoke test 6, and yeah, so all of them are real. So all roots are real, all roots are real with opposite parity. So if x0 is the root, then minus x0 should be the root, and also the other thing is that all roots are in -1 to 1 interval. They should all be there, and that's the case. Minus 0.932, minus 666, minus 0.2386, plus 0.2386, 0.06612, 0.9324, and for the odd order or odd degree, one root should always be 0. Okay, so what we are going to do, okay, let's close this, let's close the polynomial here. What I'm going to do, I'm going to say for int, so all of these roots are real. C roots dot length I plus plus points I is equal to C roots I dot real. get real, which returns a double value. All right, we get the points, we get the weights, and then we get the results. Now let's just print the weights and points to make sure that our algorithm is correct. So we do a sysout on, let's say, arrays to a string of a double let's go to the arrays class. It has two string methods, int char byte object. So we're going to a string points, and let's call this points equals plus arrays, and also weights. All right, now let's create a new test class, test Gauss-Legendre or test quadrature with a main method. I'm going to create a test, public static void test1, and here I'm going to invoke test1. All right, and now in the test1, what I'm going to do, I'm going to create an integral, or maybe create an integral function 1D. Func t goes to t times t, for example, and then I'm going to create an integral 1D integral finder, new integral 1D. I'm going to pass in our integral function, and then double integral or double result is integral finder dot Gauss-Legendre 5.3 just Gauss-Legendre 0 to 4, let's say 3 points, which we already know the coefficient. Sysout on the result. So the points, the result is 21.333, and this should be exact because a 3-point Gauss-Legendre quadrature should be exact for polynomials up to so let's just also calculate the exact. So it should be exact for up to twice the degree minus 1, 2 times 3 minus 1, 5th degree polynomials. So the exact is math dot power of basically 4 to the 3. That's just 4 times 4 times 4 over 3. Yes, so the exact is, and then we get the points and weights, and let's compare them with what already we had in the table before. Okay, so points are 0, and its corresponding weight is 0.8888, which is 8 over 9. All right, and then we have plus and minus 0.774597. The most accurate one is 0.77459666 is. All right, and then its corresponding weight is 0.55555. So here 0.55555, so which is 5/9. So that's the corresponding weight, which is accurate. Now let's try the third degree. Let's try the fifth degree, the 5 or 4. And these are the points and weights. Okay, let's compare it. For we don't have any zero, we have plus minus 0.33998. Here we have plus minus 0.3399981, all right, and plus minus 0.861136. okay, and the corresponding weights are 0.652145, all right, and then 0.347855. okay, so our Gauss quadrature seems to work just fine. Now if you recall, when we were testing the integration, what we said that is the problem is that if the interval is long, very large, let's say from 0 to 40, the error of the Gauss quadrature scales up with because of this scaling factor b minus a over 2 and the mapping that happens from ab to minus 1 to 1. The error scales up, and then there are several ways to compensate for that. One is basically, as we increase the number of quadrature points, the number of terms, the error goes down. So we can in fact increase the number of quadrature points. So Gauss 3, I'm going to call the Gauss here, Gauss-Legendre, with the number of here, let's say 40. Points. So 3 points, 5 points, 40 points. And I'm integrating t times sine of t from 0 to 40. So let's see what happens. So this is our test 4. So as you can see, the 40-point quadrature is still working. So it's takes some time to find the roots. So that's not the best way to implement it. So let's implement, let's say 5. Okay, let's also comment this out, so we don't want to print the. So the 5 points are basically the same, which is not good. Let's go 10 points. Not good. 15 points. It's getting better. 15 point is getting pretty close. 27.5028. Simpson is 4228. Let's go 20 points. 27.389. We're getting closer. 25. No, it's getting worse. 35. Now it's taking a lot of time. So definitely it's not a good idea to try to just increase the number of points, right? So what is recommended here? To stick with a smaller number of points, let's say 5 points, all right? And then instead of increasing the points, divide the interval into smaller sub-intervals. So I have this Gauss-Legendre, and that tells me the quadrature point, And then what I can do, I can define another method, public double Gauss-Legendre, double start, double end. All right. And what I'm going to do here, I'm going to do something similar to what we did for example, for forward rectangle, just a simple summation. So what we're going to do, break the interval into a smaller sub-intervals, and then use 5 or 10 point Gauss quadrature. Now if the interval is small enough, 5 point or 10 point are pretty good, and they're pretty fast, right? So we even have the basically exact roots for, we don't even need to calculate the polynomial and find its root, we already know them, right? So what we can do here is so I'm going to define a sum which is 0 originally, int num intervals is let's say we're going to break it into 100. All right, and then we're going to have the x endpoints, which is I'm going to use from math utils using the linear space, or we can just define our delta x, double delta, which is end minus start divided by num intervals. Okay, and then in each sub interval, so I'm going to create double x, which is a new double num intervals plus 1, and then for int I equals 0, I less than x, I plus plus. And actually I don't need that, so I just write the for int I equals 0, I less than num intervals I plus plus. I do the summation and call the Gauss-Legendre 5 point start. My start is basically start of the interval plus I times delta, and the end of the interval sub interval is start plus I plus 1 times delta. Okay, and then I return the sum. So what I'm doing the same routine, dividing into sub intervals, but in each sub interval I'm calling the 5 point Gauss quad instead of Simpson or trapezoid. Gauss quad method. All right, let's test this one. So we have a 40, okay, and guess 4 Gauss 5 point sub intervals. Gauss-Legendre. So remember, I'm breaking into 100 sub intervals, and it pretty much is pretty fast, because 5 point Gauss quadrature is pretty fast. All right, and now we have sub intervals, so in each sub interval we calculate it and then we sum it up, and it's roughly similar to the Simpson, 27.4228563. all right, so they're pretty close. And let's just look at the sign. This is a periodic function, so let's see what happens. Forward approximation is not good, backward not good, center, trapezoid 1.644, Simpson 1.66695, and Gauss 5 point with subintervals is 1.66693. So it's pretty close to Simpson. All right. Now this should be more accurate if we increase the number of points here. So instead of basically if I go here, instead of having a 5 point, if I call the Gauss-Legendre and let's say 10 points, okay, then each time, the problem here is that each time I'm calculating the points and weights again, which is not efficient at all. So that's not a good way to do this. It's better because the points and the quadrature points and weights are fixed for 10 points, right? No matter what the function is, no matter what the start and end is, right? So this is not an efficient way to do it, but let's just try it. 1.6669379. So this has to be the most accurate one. And if we go back and change it to 5 points again, Gauss-Legendre 5 points. So here the weights and points are fixed, so we're not calculating them. It's still the same, right? So the 5-point Gauss quadrature is accurate enough. Now you can make it in a bit more adaptive in terms of keeping track of the convergence instead of having to set the fixed number of intervals or number of points. So if in my math lib class I have in the integral package, I have this integral 1D class, and it's more of an adaptive integration. So I start with 10 sub-intervals. So I break the original interval into 10, and then I start with 5 points for Gauss quadrature, all right? And then I set a limit for the maximum number of iterations. And then what I do here, in the get integral, I look at the absolute error, and then also make sure that the number of intervals is less than some max number of iterations. So if the convergence is not reached, I increase the number of intervals by 10. Okay? And then all right, and then in each sub interval, I do the Gauss quad with the number of points, which is initially set to 5, right? So I'm doing 5-point Gauss quad with an adapting way of increasing the number of intervals. So if with the original 10 sub-intervals we don't get a good convergence, I increase the number of intervals by 10, and then I increase the number of iteration by 1. So in each iteration step I increase the number of sub-intervals by 10, all right? And then I compare the current result, the new result, with the old result, all right? And if the difference is basically less than the error bound, then this is basically the relative error. Then I call it the convergence, okay? If not, I continue until either the convergence is reached or I hit the maximum number of iterations. But the Gauss quad is always kept at a fixed number of points, which is initially 5, and you can change it using this setter function, all right? Okay, so the last thing that we're going to discuss on this topic is the other types of quadrature. So we can generalize this quadrature concept, and the reason is that sometimes we have some integrals that the function f of x, even if I'm integrating over -1 to 1, the function might have some discontinuity at one of the two ends. It becomes it has some singularity, right? So if f of x has some singularity, over the a and b interval, we cannot directly map it to -1 to -1 because then one of these two limits or both of them could be the singularity over -1 interval. Or sometimes one of these limits of the integration a and b are infinite. A could be -infinity, b could be +infinity. And again, for these cases, the Gauss quad doesn't really work. So what we need to do, we can define a weighted integration. So the idea is that instead of integrating f of x dx from a to b, we integrate a to b w of x f of x. This is extremely important when we're dealing with the discontinuities of f that go to infinity. Then this weight function can regulate them, and more likely it can suppress those very high irregularities in the function values. Okay? So we're going to calculate this weighted integral using quadrature method instead. So instead of calculating integral of f of x, we calculate wx f of x. And there are ways to choose this weight function based on the type of singularity that the function has. So if the function doesn't have any singularity over a and b, it's well defined. So when we map it to -1 to 1, the function is perfectly defined in -1 to 1, also at the edge points -1 and 1. And therefore the weight functions are 1, and the orthogonal set of polynomials that we use to find the weights and quadrature points are the Legendre polynomials, as we saw previously. But if f of x has singularities at both endpoints, then we can use Jacobi polynomials. Or another type is Chebyshev polynomials of the first kind. All right. Even if the function doesn't have any singularities, we can still use the Chebyshev polynomials of the second kind. It's still fine. We can find the weights and the quadrature points. If we are calculating the integral from 0 to infinity, so infinity is automatically a singularity for the function, right, for the integration. In order to suppress this, especially if the function goes to infinity at the infinity, we can suppress those fast growing values by a fast decaying function, which is e to the negative x. And this results in the Laguerre polynomials for the orthogonality. And the orthogonality is then defined based on this weight function xk pn of x. All right? Or we can choose, if we are doing -infinity to +infinity, we can have a much faster decaying function, which is e to the -x squared. This is a Gaussian function, and the orthogonal polynomials for determining the weights and quadrature points are Hermite polynomials. All right? So the idea here is that if the function has singularities, which are most likely of type infinity, so if f goes to infinity, that's the main problem with the integration. If f has singularities but it's not infinity, it just happens to f not being defined at some discrete point, it doesn't matter, the integration doesn't matter. But if f goes to infinity, we can use this weighted integration and suppress those high values by choosing a decaying function. All right? So this was the main idea of quadrature methods for numerical integration, and they are the most widely used methods when we deal with numerical integration. Thank you for watching, and I'll see you in the next video.